Hi, ladies and gentlemen, here we go. Let's go to a few things to remind you guys here. Tomorrow is your final exam. It's a 2 hour short exam. Okay. So I'm going to remind everybody here a couple of things I did here. I put up a study guide for you all, and hopefully there's enough bandwidth. Oh yeah, there is. Okay. So here's a study guide. And I want to remark, I did modify it. I did delete a few things, but I also added a few things. So it's just modified. This is one thing I added because I've always wanted to get to do that, and I did that yesterday. So what I added was a hypothesis test about a mean, but notice it's with data. Okay, so you say, what do you mean it's with data? There's a list of data. So that's what I added. I'm going to talk a little bit about the aspirin and heart disease kind of question. And I'm going to talk about the IQ test for men and women. So I put that. I kind of like this one. And I also have another IQ test for men and women. One's a hypothesis test comparing two means. One is a hypothesis test comparing two proportions. And then, of course, we have the linear regression and correlation we have to talk about this morning here. So I did modify that for you as well. I also did another thing. Did anybody notice anything? I sent it to you guys earlier today. What did I send? Did you guys notice? This morning. I sent, let me check it. Yeah. I sent you guys. What did I send you? Do you notice? Yeah, thank you. I sent you guys. Title. What is. Okay. Let's put a title here. That's odd. So let's put the title. Sorry, no title. That was titled key phrases. And yes.
I can remember formulas, but it comes down to just the keys.
84 plus. I don't know, not a formula sheet. What do we call it? Summary sheet. So I already sent this to the school to print it up for you guys. So it's available for you on your final exam. Okay, so let me share with you what it is. I put copies here. And I also placed it, so I want you guys to look at it, by the way. And I also placed it down here. So let me I'll do the key phrases first to remind you guys key phrases here, okay? If you can see that. Okay. So here, all right, here's a key phrase sheet I'm going to give you guys on your final exam. Like, people may not know what does between A and B mean, right? Between two numbers, right? So I actually put down the phrase between A and B. What is really short for that X is between A and B? It's the interval between A and B, right? I even put down here at least A. That means X is at least A. That's the phrase. So that's why you see this X greater than or equal to business there. So here, let me scroll in, but you guys have those key phrases. I did say I was going to try to get that up. More than A, X is more than A, so X is greater than A. Less than B, it's really short for X is less than B, so X is smaller than B. No more than B, X is no more than B. It's X less than or equal to B. And then something like this, A is B, that just means A equals B. And then you have A is not B. Okay, so it's not equal. So what I put up there for you guys, again, is some key phrases. That you'll have that sheet for your final. I also put up for you guys, in case you said, hey, there's some, it's turned into a data entry processing kind of course, right? A TI function course. So I created this morning here for you guys as well, okay? This is a summary sheet for the TI functions that we've been using here. So it's like entering a list of data. You go to stat, edit, right? Sorting data, stat, edit, sort. So I want you guys to just double check to see if I'm correct with this. And then what is that? Computing a single variable computation that we do. Stat, edit one variable. That gives you the mean, median, the mean, median, first 5-number summary, standard deviation, blah, blah, blah. So, you have the summary sheet for your TI, right? And then I made for you guys here the binomial, which is second distribution binomial PDF, Poisson second distribution binomial PDF, a normal distribution, second distribution normal CDF, normal distribution working backwards. That's the inverse norm, right? Second distribution inverse norm. So I created just a summary sheet of those functions that we use. Estimating a proportion. Now, when I say a proportion, that's one proportion. And so it's stat test one proportion Z interval. Estimating a mean, large sample. Stat test Z interval. Estimating a mean, small sample. Stat test T interval. Okay, even have a picture. Hypothesizing about a proportion. I put for the critical value, second distribution inverse norm. Stat test one proportion Z test. So as you guys see, what am I doing? I'm giving you guys a summary sheet of your what? TI functions that you'll be using on your final as well. Okay, so hypothesis about a mean large sample, how to get critical values inverse norm, stat test Z test, and then hypothesis testing about a mean small sample. Remember, you do the inverse T to get those critical values, and then it's stat test T test. Hypothesis about two proportions. Again, you use the inverse norm to get your critical values, but you're going to use stat test two proportion Z test. So this is going to be, again, the what? A summary of what you do. And then hypothesis about two means critical value inverse T and the stat test two sample T test. And then we'll have what we have today. Okay. So you're going to have this formula sheet with you. There's no need for you to print anything up, just so you guys know, but you're going to have both of those sheets. Okay, you guys okay with that? Sorry, that's the wrong button. So instead of giving you a formula sheet, this is now the summary TI sheet, I guess. Okay, so I made that for you guys this morning since I get up early. And I try to get some work done, okay? So I get a lot of work done in the morning and then later at night. So this is what you guys have on your test. It's a summary sheet. Do you need to print it out? Say what? No, you don't need to print it out. Who's going to print it for you? I am. You guys are going to have it. And I even put the pictures. I wasn't going to put pictures, but I decided to put the pictures. I don't know how you guys feel. Pictures okay? I don't know. So I was just going to put the list of everything, but I said, I'll put the pictures next to it.
So it's going to be one on each page? Are you gonna...
Just like what you see here. It's exactly the sheets you see here. These are PDF files of those sheets. So, instead of saying, okay, I'll give you a formula sheet, but you don't even use the formulas anymore, you're using the TI functions. So I guess it makes sense. It's kind of like a weird, I'll give you the formula sheet, but you're really using TI. Very inconsistent. So just trying to get some consistency here. And in the future, I think I'll be taking a course in Python, and I might be even having some Python stuff here. Just so people know, that's kind of on my to-do list too. So anyway, what are you guys at home? You guys, those bonbons, you guys sitting on the couch with the bonbons, you guys okay? I hope so. So anyway, because it's kind of a weird thing that if people show up tomorrow for their final and they don't even know they can use this stuff. It's like a weird, wow, don't know what's going on, It's like a whoa. I woke up and did this for nothing? You're like, you did all that work for nothing? People look at me like I'm crazy. They go, why are you doing all that work? It's like, well, because the programmers that wrote it, I would be happy if they actually can describe it a lot better than they do, or even if they were a little bit more consistent with the phrasing they use. It's like a weird program. Like if you spend all your time thinking about why did they name something the way they did, I mean, sometimes it's makes sense, and then sometimes it doesn't. So, and if they're inconsistent, you want to know why were you inconsistent. But anyway, we just have some good mornings. Yes, it is. Okay, Cassandra, I'm glad you appreciate it. Okay. So, all right, let's get to what we want to finish off. And believe me, this is a process, and it's an important process. So in the notes, if I'm here, I'm going to go back to this other website here. And down here to linear correlation and regression. I did these notes for years. I'm going to put it in the chat. We got to talk about this phenomenon because it's highly interesting. And you guys might definitely see this in other classes. Linear correlation and really regression here. So I put that in the chat for you guys. I have it here in the iPad, and so I want to share with you guys this very important topic here. Okay, maybe you can see it better this way. Now, linear correlation. Now, first of all, what I want to say to you guys is this. This borrows from kind of like beginning algebra, in the sense that we have what's known as, I'll give you the definition here. We call this bivariate data. So now what you're going to do is you're going to collect bivariate data. So let's go through the words here. Right? Bi means two. Variate. Yeah, variables. So it's two variables. It's always good to look at a word and try to figure out what that really means. Two variable data. You go, wait a minute, I had trouble with one variable, now I have two? Yeah, you have two. And when you're talking about the two values from algebra, you guys remember you have like an x coordinate and you have a what? Y coordinate? Okay. So we're going to have two coordinates here. So there's no coincidence that I raise up this. This is a point in algebra. So it's a point in algebra, x and y variables here. Now, one of the variables is called an independent variable, and that's a variable, the first variable is thought of as being an independent variable. And this is a dependent variable, meaning supposedly you can control the x value. This is the one you could control. It's independent. This is the one you can't control. And I'll share with you guys why. Okay? Because what's really under the hood, in all honesty, is really this phrase here. It's algebra. Okay? Beginning algebra. So to remark to you about this process, to kind of give you a summary of it, what you're really looking for is this. If you say, why do they call this topic a linear correlation, right? Well, you want to think of it this way. The real question that we're going to really ask is this. This is a big question. Is there a linear relationship between the two variables? Right? Between these two variables. Is there a linear relationship? Now, when I say linear, I mean what? Linear. You say, what do you mean by linear? This linear relationship? Well, go back to algebra. You have this y equals what? mx plus b. That being a linear equation. So if you guys remember from algebra, you know, y is mx plus b here. That was called a linear equation. And it's in two variables, x and y. And in fact, it's particularly what's called the slope-intercept form. Okay, so there's a very, very intimate relationship between these variables, hopefully. And we want to find out, is there a linear relationship? Do you guys remember what this M stood for, by the way? You guys remember M from beginning algebra? What was M? This is a slope. Yeah, that's the slope of the line. Okay, that's the slope of the line. So, yeah, this kind of goes back to beginning algebra. Okay, now let me do something here since I'm giving you guys like the background here, because the background is always important. So let's get this template out. Background information. Now, you say, okay, you're gathering data. And way back in beginning algebra, remember, you guys plotted data. Is that right? Remember you had plotted points? It's your x-axis. Here's your y-axis. So here's kind of what we're thinking of in all honesty here. These are all data values, x and y. But in statistics, we call this a scatter plot. Okay? A scatter plot is simply the bivariate data, is when you plot bivariate data. So you plot that bivariate data. Remember, x versus y, two variables. And what you hope to see is a pattern that aligns with a linear equation here, okay? So what you guys see here, this is a line L, okay? That's the line they're talking about. That's your linear equation. And that has a format of, or is represented by y equals mx plus b. Okay? This here, this equation, yes, it has a slope m. This is called a few things. This is known as what we call the best fit line. So you can actually see language that says, oh, this is the best fit line, but it's also known as the regression line. Okay? It's called a regression line. Now, this is a very fundamental entry into this topic, because you might say to me, what do you mean fundamental? Well, there's a lot of equations and functions that you might see in a math course. You have things called quadratic functions, exponential functions, logarithmic functions, cubic functions, polynomial functions. Data can fit a lot of other different types of functions. You can gather data and you go, oh my God, that looks like maybe a sine curve or a cosine curve. Oh, it's not all linear. So phenomena isn't related to one another in a linear way, generally speaking. It could be related to one another in terms of a quadratic, a cubic, exponential, logarithmic. Okay? However, we're starting to look at data in this way, bivariate data, and you're trying to fit the data to this regression line. So in other words, it's kind of the most fundamental bivariate model you can consider, at least in terms of mathematics. And you might take other courses where they say, okay, your data fits these other functions. But, you have to start somewhere, and you start with that linear regression. So it's a very classical scenario, linear regression and correlation. And it's all goes back to that algebra course. Hey, can you plot an x and y coordinates? Yes, we call that a scatter plot in statistics. Hey, does it look like the data can fit in a line? If the answer is yes, well, then there could be a regression line, but it's a process. Okay, you guys okay with that? It's a process. So here's what I want you guys to note here. Just some terminology here. Note. We can have a positive linear correlation or a negative linear correlation. Okay? The correlation could be either positive or it can be what? Negative. Now you might say, why is that? Why do you think you can have a positive linear correlation or a negative linear correlation? Does anybody know? Well, no, but we're going to get to that. There's another term for that. But here's what I'm saying, and here's a big hint. Because of what? Your slope M could be positive or negative. Well, uphill. You see this, what you're looking at? The slope here, by the way, M is positive. So that's an uphill. That's all it is. It goes back to the algebra.
So more x, more y, or more x means less y.
Just increasing slope, uphill. So I'm going to put that here, uphill. Huh? Oh, yeah, that's all we're saying. Is it, the slope of your line could be what? Positive. If the slope's positive, right, going uphill, we say there's a positive what? Linear correlation. That's all. The other scenario is when you draw lines, is it could go downhill. You say, what? Yeah, you can look at everything the same way. Just because you have data doesn't mean it's going to, and you plot it, first of all, it doesn't mean the data is going to fit on a line. It may not fit. Okay? But your data can look like this, maybe. X value, Y value. The scatter plot. I want to get used to saying that word. The scatter plot. When you scatter the data, just plot the data. Here's L. When you plot your data, this is an example of data that fits, that could fit, well, maybe, we'll see, that can fit in a what? Straight line, but it's now downhill. So the regression line, or that equation of y equals what? mx plus b, m has a negative slope. Okay. And I'm going to color this, I don't know, pink, let's say. Negative linear correlation. Okay. So your slope is downhill. So if you put a person here, this is what I do in big, we used to teach beginning algebra, and you would have to just go downhill like that, and you go, okay, that's a downhill situation. That's a negative slope physically. Okay. So remember, you scatter your data. What's it called? Scatter plot. Okay, it's a scatter plot. And hopefully it fits the pattern of a straight line, okay? Now, I want you guys to know something here. You can scatter your data. That does not guarantee your data fits on a line. Okay? So I'm going to say there's no guarantee. There's no guarantee of a linear correlation. So if you look at a scatter plot, you might say, okay, I scattered my data. I just plotted my data on an XY axis, and you might just see things that look like this. Bivariate data. And you go, there is no way this data fits on a what? Oh, thank you, sweetie. Thank you so much. You might say that you missed the surprise I gave everybody, though. No, more resources. You could use, I gave you a TI summary sheet on your final. I gave you a summary there. See? And I gave you, what else I give you? Key phrases. Maybe I'll show you guys again and remind you, because it's good. People. Okay, well, I'll show it to you guys all again. All right. So here's this. What do we say about the scatter plot here? This is called a scatter plot. Do you remember in high school them talking scatter plots? So here's what we call a scatter plot, and we're going to say this. There's no linear correlation. Now you might say, how do you know? Well, two things. There's no linear correlation. You can't best fit that data on a straight line. Okay, you guys understand? Here, you can. You say, it doesn't look like the data fits exactly on that line. Here, it doesn't look like the data fits exactly on that line. Okay, but we can kind of draw a line and maybe fit the data there. But here we can't do that. So graphically, you can say, there's no way that data is going to fit on a line. Okay, all right, you guys okay with that? Now, that's just right off the bat. You scatter data, plot it, bivariate, two variables now, and you might discover, there's no line that we can fit that data. If that's the case, don't worry about it. You don't sweat it. If you do see the data can actually fit on a line, then, ladies and gentlemen, you're on to something. But you got to do formally the following here. So formally, I'll give you guys a fact. If data seems to fit on a line, okay, and you say, how do I know? Because you looked at the what? Scatter plot. That's actually a big part of the process. So if you do see the data seems to fit on a line, right? Then you say, what do I do? Well, then you do the following. Then you follow the formal process. I'm going to share with you guys what that process is. It's going to be pretty simple. And you follow the formal process, okay, to determine if there is a what? If there is a linear correlation. Okay, so you might say, there's a formal process? Yeah, it's actually a hypothesis test. But it's going to be easier than the other tests that you've seen. Okay, so you're going to follow a hypothesis test. There is a hypothesis test. So you might say at that point then, what is the whole point of this? So you say, okay, what is the whole point of this verification? So you say, what's the whole point of this verification? That's so you can, here you go, determine the what? The regression line. What is that also called? AKA the best fit line. And remember, that's of the form y equals what? mx plus b. That's in slope-intercept form. So the whole point for you is to find the regression line. Okay, and you go, really? That equation, y is mx plus b, that's my whole point? Yeah. Then you go, well, why do you want that line? Does anybody know why do we need this? It's a very good reason why we need this. So we can be what? So we can be predictive. You go, predictive? Yes. The whole point of this, to get that regression line, that equation, is so we can now be predictive. You give me an x value, I will give you a what? Y value. Yeah, I'll give you a prediction. That's the whole point. It's like it's like science is based on that, you know. Here's some data. What function does that data fit into or model? If you know that, then you could be predictive. Then you could use that equation in science. You know what can happen if they give you an input, you'll get an output. That's the bottom line. That's what you want to do. So that's kind of like I said, ladies and gentlemen, the whole, I would say to you, you know, rough idea behind this process is that ultimately we care so we can be predictive. We can predict the future if we know the equation. Okay? It's kind of like if I got to go to the doctor and the doctor looks at certain data about myself, the doctor, he or she, could be predictive and say, I'm going to prescribe this medicine. You're going to take this amount for you, for your body type, weight, blah, 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 whatever it is. You want to be what again? Predictive. That's the whole idea, ladies and gentlemen. That's why kind of all those equations that you know, I always hear these things like, why do I care about the quadratic equation type of thing? You know, people are arguments. It's like, well, you know, you might actually have data that fits a quadratic. You know, you could be predictive. And how would you even know if you don't even know what a quadratic looks like? Or what about all the science that's based on using quadratics? There's a lot of physics based on a quadratic. There's a lot of information. So there are people out there that question, do I really need to know some of these math equations? I just want to take a statistics course and I'm going to be brilliant. And I'll say, well, if you don't know what some of these other curves are, as you study this deeper and deeper, you know, you might not even know what you're looking at. Maybe you have the cure for cancer and it involves an exponential function, but you never knew what an exponential function was. You know, I don't know. Those are the kind of conversations I have to have. So there it is, ladies and gentlemen, just to give you guys in a nutshell. Now, what I also did is I wrote this, and this has been around for years, these notes that I started with, and under the hood, there is a lot of arithmetic. Remember I said to you guys, I had to take a course that proved everything. My statistics course, we had to prove this. We had to develop all of these equations, you know. But this is no longer needed. I used to do it the old way. You know, some of this notation-wise, sum x, you guys know what this is. N represents the number of data pairs now, bivariate. Sum indicates to add. Sum x, add the x values. Sum y, add the y values. Sum xy, add the product of xy. Sum x squared, add the x squared values, yada, yada, yada. That was all part of our past. We use the TI now. We don't actually use that. You go, oh, good, you know. We use the TI, okay? Yeah, exactly. Exactly. So I do got to give you the background. So, you know, got to give that to you. But, yeah, it's interesting. Now here's what's really going to happen here. So you guys know. Okay, I'm going to start to get into the little bit of the formality of it. The idea is that, you have a population. And all you did, remember this, all you did was take a what? Sample of data values. So you go, okay, you got a population. You take a sample of data values, all right? Now, what does R represent again? I'm going to tell you, R represents what we call, this is the definition, the linear correlation coefficient. You might say, what do you mean coefficient? It just means number. That's another fancy way of saying number, coefficient, okay? R represents the linear correlation coefficient, linear number. And, for paired sample data, bivariate data. Rho, you say, what is rho here? Well, rho represents the linear correlation coefficient for the population. In other words, this is the true value. Okay, because remember, we're only taking sample data. There is a true value, and then there is a statistic. You say, what is R? R is R in some ways is a statistic. So we've been taking statistics and we've been taking true values. You guys remember? Okay, so we have R and we got rho. That's going to be important in the formal process. Now, there are some requirements. Remember yesterday we started talking about some of the requirements that are hidden with some of the hypothesis tests. And there's actually a lot more tests in your book that you can go over, in all honesty. There's a lot of different tests. But we can't really go over all the tests. But, you guys could do some reading into other tests and you can start to see some of this, how it works. That's the idea. But for the requirements here, this says the following, right? The linear coefficient can always be computed for any set of sampled bivariate data pairs. Okay? But the following requirements should be satisfied when using a sample pair of bivariate data when making a conclusion about whether there is a linear correlation in the corresponding population of paired data. Now, these are the three, requirements. And what's going to happen is all the stuff that we do are going to satisfy the three. It's the way it works. So the sample of paired data technically has to be random. You go, okay, Mr. Judge, we know that should be random. Step one. Step two, here's what you're going to do. You want a visual confirmation. What is that visual confirmation? Scatter plot. That's going to tell you whether or not you should proceed. So you always draw a scatter plot, a visual confirmation. You want to confirm that the points approximate a what? Straight line. So that's always in the procedure. That's kind of the first thing you do. You say, okay, I got this data. Let's see if it's in the form of a line. Or let's see what other curve it might be in the form of, generally speaking. It could be in another curve. So you plot your data, X and Y. Okay? Now, if you do see a pattern of a straight line pattern, then this is what you do next, right? The results are strongly influenced by outliers. Okay, now this is something that's debated. You go, what's an outlier? Do you guys know what an outlier is? Yeah, this is something that's way off the general pattern. So this could be a data value that is off the general pattern. So this process and this test is very sensitive to outliers. Very sensitive. And you might say, okay, well, what do you do then, right? So they must be, so generally speaking, if you do have outliers, you know what they say you got to do it because it's so sensitive? They must be what? Removed. So you remove the what? The outliers is what you're saying. You got to throw those outliers out. Generally, you don't want to ever throw out data, but in this case for bivariate data, say remove the outliers, okay? So at times, we may calculate the linear correlation coefficient with or without the outliers when considering a linear correlation. So at times, you might even keep them. Other times, you may say it's best to throw out. And then, of course, when you write a report, you can argue why you think that might be the thing to do, or you can argue why you might think that you want to keep them. That's kind of how it works, because when you look at your data, people might see, oh, you got some outliers. Is there a reason why you kept them? They may want to know. Is there a reason why you throw them out? You want to justify it. So that's kind of what goes on in like a formal report if you do those kind of things. You consider the outliers and you may remove them or you may not. Here's the other last thing. Formally, we require both variables. Both variables, X and Y, have to have a normal distribution. So in other words, if you looked at those two variables, and that's where, you might say, how do you know if the distribution's normal? Well, that's when you might use the box plot. So people sometimes use box plots for those. So you might look at that and go, oh, is that why we drew a box plot in the past? Yeah. So you go, okay, you can verify that both X and Y are what? Normal. And if they are, this is called bivariate normal distribution. Both variables X and Y have a normal distribution. So you just look at them actually separately. So that's kind of the formal process if you guys wanted to know. If you're going to take another follow-up course and they talk about some of these details, they go over these details. But that's why maybe you want to consider, okay, let's look at the box plot and see if most of the data is in the center. If it is, it's normal. So those are the requirements. All the examples that we see are going to satisfy that requirement. So you go, oh, okay. Is that what they do? Yeah. Generally, they're not going to throw you a curve here. And they go, sorry, you didn't, check that y was not normal type of thing. That's another kind of course. Okay. It's not your elementary statistics course. So these are really the requirements behind what we're going to do, this procedure. Now, again, I got to go over this. The TI is going to take care of this. So you're going to enjoy the TI. Going over the process only takes like minutes. Let me rephrase that. Going over the TI calculator takes minutes. But going over this process, you just want to give people that background. So here's what we call the sample linear correlation coefficient, R. In the old days, that was the formula students had to use. And you go, really? Yeah. So I actually, like I said, I've taken courses where you had to prove that formula. You have to derive it. Yes.
So during the spring semester, will you be covering the formula, or is the spring semester all calculated?
But I would say this stuff is kind of everywhere. You can probably Google it. I'm trying to remember what video, because I used to teach it. I'm trying to remember where I put the video. I actually, when we did this, I would do this. I would actually, you know what I would do? I would teach the course with a Microsoft Excel spreadsheet. So here's my X value, here's my Y value, and then sum all these things. And then on an exam, you know what I would do? I would give them the spreadsheet. So they would have some X, they'd have some Y, they have some X squared, some Y squared. They had some XY. They had all of that. They just had to plug it in. But, and then they felt like, oh, okay, good. That's better. But yeah, that's how you compute your sample linear correlation coefficient. Other courses may have you do that. But yeah, that was what we used to do. And I guess I've taught the course where, but I'd give them an Excel spreadsheet and I'd lecture with Excel. It's easier to see how to do that and compute it. Excel actually has a built-in function that computes R. Excel can compute it. Okay, so I would just have to highlight my X and Y values, and then I'd hit. I think it's called. Remember the name, but there's a function built in Excel that actually computes R for you. There's software that computes R for you. I'm even bet. What's that software that everybody uses now? Desmos. Desmos might have that built in. I'm gonna have to look at that. Note to self. I gotta. Yeah. I use it for the other courses, the STEM kind of courses, algebra. I'm going to put that in my notes. Desmos and stats. Did you say that has a box plot there? That's nice. That's the one thing Excel doesn't have. Huh? Yeah, I used to do this in Excel. I'd show them linear correlation, that line, but we're going to have TI. TI does it too. So, but I do have to go over. I do have to scare you because then you're appreciative. You know what I mean? It's kind of like if I said, "Hey, you guys are gonna have to run 5 miles up that hill." You wouldn't mind. But then I brought out a golf cart. You know what I mean? And you're like, "Oh yes." It's you're right. Right. Yeah, I'll see you guys up there. Yeah, exactly. So here's the deal, right? Here's the fact about R. R is going to live between these two numbers, -1 and +1, okay? And it measures the strength of the linear correlation between the quantities. Strength. R is very sensitive to outliers. Remember, this whole process, outliers, it's very sensitive to outliers. A single outlier can dramatically change this value. That's why you throw them out. You say, I guess there was an error somewhere. Throw it out, And then you compute a test statistic. You go, yeah, we've been computing a test statistic T. And yes, it's a small sample because we're not doing large samples. Remember this? So generally speaking, there is an exception, but we're going to do a small samples under 30, okay? And it's used to test whether there is a significant linear correlation between the two quantities. Now, I want to say this. R, if you're close, if R is close, really, let me say this. R is generally close to 1. Okay? R, you're looking for, is close to -1. And this word close, you're like, well, how close? The closer you are to a +1 for that R value, since it's between -1 and +1, the closer you are to 1, the stronger the linear correlation. Okay, the stronger the linear correlation, and it's a strong positive linear correlation. So that's one situation we want to think about. If you're very close to -1, well, then you have what's called a strong negative linear correlation. You go, why negative? Because it's downhill. So remember, this one is the uphill scenario. Positive R. This is a downhill scenario, negative R. So that's why R is going to be close to +1 and -1. That's going to even be verified by the scatter plot, you know. Very, very beautiful kind of process. Okay, now we're ready for the formal process, okay? And it's not going to be that hard because you get to enter everything in the TI. But let's look at how this is formally done, okay? So remember, you did a scatter plot and you found that data, what? Looks like it could be on a line, either uphill or downhill. And you go, I'm going to proceed. I'm going to test to see if there is a linear correlation. That is the test. Is there a linear correlation? So remember what you do with hypothesis tests? You have a what? You have a null, and you have an alternate. So this is always how you set it up, okay? This is what you always use. The null will always be rho equals 0, and then the alternate is always rho is not 0. Now, the numerator is your conclusion that there is no what? Linear correlation. So if your hypothesis test verifies to really accept the null hypothesis, well, your conclusions, there is no linear correlation. Rho is 0. If your linear correlation is not 0, and it depends on how much it's not, really, then there is a linear correlation. You're going to see the process. Okay? So this is an automatic setup for the formal process. Always what you use. And again, you say, what am I going to use? We're going to use the what? T distribution. This is a small sample again. So you're back to thinking tiny sample. And your test statistic will be used to determine whether there is sufficient evidence to support the claim that there is a linear correlation. So here's going to be also your claim, just so you guys know. Okay, you're going to see that. All right, test to claim there is a correlation between the two variables using alpha either 1% or 5%. So these are the standard alphas. Okay, and they're going to tell you your alphas. Always your level of significance. This T, like I said here, T is a what? This is the test statistic formula based on the value of R. Okay? So this was the classic formula students used. Not anymore. Yes, you had a degree of freedom. Don't know what color to use there. Maybe it's degree of freedom. Let's use, I don't know, pink. The degree of freedom is n-2 in this case, not n-1. Again, a theoretical result goes beyond the scope of the course. People who prove this had to use all that kind of information to make it valid. So yes, if you majored in math, you took a lot of math, calculus 1, calculus 2, advanced calculus 1, and even a proof course, by the way, and then you took your first statistics course. All proof. In other words, you derive the formulas now. And it could be done. I did it. So people do it. It's just you got to have the right prereqs. You got to have math information. You got to have the algebra that they're trying to deny students now with to derive it. Okay. So we're math people are going to be dinosaurs one day. We're going to die off. And then the world's going to discover they're going to need us again. Yeah. And then it starts again. It'll start all over again. Life will start over again. Mr. Judge will be long gone. I will be. Hopefully my videos will be online in the internet forever. They go, hey, yeah. Oh, but actually, you got it. That's a whole. There's books on this stuff. It's not out of imagination, where people discover, hey, what's the magic that was used to do arithmetic? How did they know arithmetic back in the day? Because everybody was used to using calculators. There's books like that.
Arithmetic tables in medieval times.
No,
Wooden calculators. They didn't actually know arithmetic.
maybe not.
It was like this weird.
Maybe not. Yeah, it's like this voodoo. It's like kind of when people say to me, this is always gets me when they say, well, why do I need intermediate algebra? And I say, well, you know what? Can I ask you a question? And I say, yes. If you measure horizontal distance, right? And this equals 1 unit. And I got to draw a better picture. Because I've had these discussions, believe it or not. If this measures 1 unit and this measures 1 unit, can you tell me? What does that measure? You ask these questions, you're going to get a bunch of answers. Some people say, I know it measures 3. No. I know it measures 2. No. I know it measures 1. No. What does it measure? Does anybody know? It is the square root of 2. Okay? Now, here's the thing. You go, square root of 2? Yeah, that's diagonal distance. This is diagonal distance. The Pythagoreans, it wasn't Pythagoras, even though they name it Pythagorean theorem. There were a group of people that discovered this. There's whole books on the proof of the Pythagorean theorem. This is ancient. This isn't modern information. But what you learn about the square root of 2 is it's an irrational number. And so the irrational numbers were born. And people wanted to learn about irrational numbers. They're part of what's called the real number line. It's part of what we learn and study, this real number line. Okay, because the rationals and the irrationals compose your real number line. So what I say to people like a course like intermediate algebra, why you care about it, is because it talks about irrational numbers and your real number line. We're starting to learn about nature around us, something that's ancient. So it's philosophical, very philosophical. Some people say, why do I care about these numbers anyway? Yesterday, I lived all day. Yesterday, I didn't have to use the square root formula or quadratic formula to compute, to determine an irrational number. So why does it help me? I don't know. What do you guys think about the argument? Why does it help you, or why may it not help you?
Even people in blue-collar jobs, sometimes it helps being the guy that knows some math. There's things like that, diagonal measurements.
Yeah.
Circular measurements as materials.
Yes, exactly. That's what I say. Exactly. It's like, you mean Jesus Christ was a carpenter. You know what I mean? You mean you can only build things that are horizontal or vertical? You'll never have use for a diagonal distance in your life. How do you know how much wood to use and cut? That there are reasons to articulate numerically what that value is. Is that the ghost? Was that you, or was it my bag? I don't know. That was the bag. Some of you guys are wishing bad things. Is that right? You're talking irrational numbers, Mr. Judge. You go off on that crazy tangent of yours and how maths describes the world around you, but nobody cares because some people think the world's flat anyway. So, and those people that think the world's flat, they're living pretty good. So what do they need to have knowledge and information for anyway? Why does it even have to be true in our day and age? Yes, you got social media. That tells you all the history and news you need to know. You guys know what I'm saying? Yeah, that's people say, I only look as far as Twitter, and whatever I read there, it has to be the truth. You guys know what I'm saying? Yeah. Don't know. Anyway, I apologize for the tangent, but I think it's useful, just so you guys know. Remember that one. Yeah, I don't know. Yeah. Oh my, well, those are, I argue with people. I don't want to say too much at home, Don't, what's some of the stuff I try to, well, yeah, you don't fight, how can I put it? You don't fight over everything. Well, I have rules at home about food. I'm a real weird, because I took a science course. Leftovers, I don't want like if you go out to a restaurant and you have dinner, but yet you're going to go watch a movie, maybe do a little shopping. In other words, you're not going to get home really quick. And then they say to you, hey, do you want all these leftovers? I think to myself this. I won't get home till what time? It's going to be in my hot car for how long? I'm never going to eat it because I know I'll get sick. Bacteria grows. So there's like rules and timelines that you want to do things. And then when you keep food in the refrigerator, there's rules there too. You don't keep them longer than like 2 days. Leftover food that you make. So I remember even going to my grandmother's house, and I remember I taught her how to make spaghetti the real way, or not the real way, but the non-weenie spaghetti version, So anyway, I did that, and I remember I'd go, and my grandmother just went crazy making spaghetti. And she'd say, Daniel, do you want some spaghetti? I go, sure, Grandma. When did you make it? Well, last week. I'm like, oh, my God, no. So I'd tell my grandmother, no, you can't have it you can't be in the refrigerator for 5 or 6 or 7 days. You got to get rid of it. It's bad. You're going to get, you can't. I'm going to say, Grandma, did your stomach get hurt when you ate it? How'd you feel? Stuff like that. So, there's just rules. If you're going to keep it longer than 2 days, what do? Freeze it. You freeze it. Yeah. So anyway, a little bit of science. And sometimes it drives me crazy. People that I know at home, close to me, they throw science out the window. They throw science out the window. You go, my mom does it all the time, so therefore it has to be okay. Just because your mom does it doesn't mean it's okay. It's like my grandmother and her week-old spaghetti. You know what I mean? That's true. Anyway, back to the process. Did we give you enough of a relief? You guys ready for the process? Here it is. If you guys noticed in this, what kind of test is this? How do you know it's two-tail? Yep. Not equal says two-tail. This is always how you set this up. It's not what you think. You're not reading a hypothesis test and it's going to say it. It's not going to say anything like that. It's just an automatic format, okay? It's under the hood. This is a formal scientific version of the format. So it's a two-tailed test, and as you guys can see, here's your what? Alpha over 2. So it'll give you a level of significance. Half is in the left tail, half is in the right tail. As you already know, what goes on in the middle? Do not reject the null. It's between your two critical values. How do you get the critical values? Small sample. Inverse what? Inverse t. I put that in the notes. Generally, with one exception, but I won't bring it up. You get your degree of freedom, by the way, here is going to be n minus 2. So, okay. Just to let you guys know, again, this is the formal process. People had to compute R. They go, you made me compute R? Yes. You made me plug it in here? Yes. And I know the sample size N? Yes. And then they computed the test statistic T, and then they found where it lived on the decision rule. End of story. You can now go home because you have the process, right? But the devil's in the details. Let's see how to do this in the TI. All right? And I'll remind you, before you guys faint, that Mr. Judge, go back. Let's remind you. You see this? I sent it as an announcement. You guys are going to have what here? This is your TI calculator summary sheet. I haven't put pictures. Well, I'm going to give it to you on the test. I'll print it out. I've already hit the school. I sent that this morning. The school already emailed me and said it's all done. So, okay, you guys okay with this one? So this is what I'm saying. You're going to have a summary sheet. Huh? Thank God. No? Okay, well, yes, thank God. No, don't thank me. Thank God. Trust me on that one. Thank God. Exactly. And yeah, I understand. So let's go to where do we go to? Yeah, we're on the right. Okay. So now let's see what we do. Ready? Let's do an example. You go, Mr. Judge, can you go over an example finally? Yeah, here's an example. Okay. It is car weight and fuel consumption. You may not realize this. Some people do, some people don't. Have you ever, they used to have heavier cars than they do today. Trust me on that one. The cars my mom drove, all cars were very heavy. As a result, fuel consumption wasn't that good. Okay, historically. And as cars have gotten lighter, fuel consumption has gotten what? Better. So you're saying, what do you mean? Is there a correlation between what? The weight of your car, this is car weight, and what? Fuel consumption. What is fuel consumption? Yeah, it's essentially how much fuel your car uses. This is generally done in MPG, miles per gallon. Now, what I want to remark about is this. In theory, you can control the car weight. So it's kind of like the designers of a car. So here's the X variable, the car weight, and then it's followed by the what? Y variable, which you can't really control, which is thought of as the fuel consumption. So here's my bivariate data, okay? Everything in orange is an X value. So if the car weighed 3,175 pounds, you know what MPG it got? 27 MPG. Okay, see what I'm saying? If the car weighed 3,450 pounds, it got 29 miles per gallon, MPG. So the question's going to be, is there a linear correlation between the two? Okay. So remember, the process is always what? What's the first step that I said you do? Scatter plot. Scattered plot. If you don't see a correlation in any way, then you stop. Why would you go further? You're not going to get an equation. I mean, you can, but it's not going to mean anything. So here's what I'm saying. You got bivariate data. Now, notice what they say. The bivariate data listed below are the weights in pounds and the highway fuel consumption amounts, MPG, of randomly selected cars. Is there a linear correlation? Here's the question. Between the weight, that's the X value, and the highway fuel consumption, and then that's your Y value, ladies and gentlemen. And alpha here, they told you, they're always going to tell you alpha. Alpha's here going to be what? 5%. So I'm going to say the first thing you do, always, is the scatter plot. Scatter plot. Scatter your data on the XY axis. The good news is you don't need to get graph paper to do this. We're going to scatter this. But notice we have what does bivariate mean? 2 variables. Okay? So here's your step 1. And here's my point. I'm going to share with you guys how to do that. That's actually not on the TI, by the way. I forget. That might be Microsoft Excel. Step 1, plot the data on a scatter plot. See if the data is in the form of a straight line pattern, and to determine if there are any outliers that need to be removed. So what do you guys think? This is how the data was plotted here. Can you fit that data on a straight line? I think so. And I don't know exactly how that line will look, but it could look something like this, if you guys see what I'm saying. So what I'm going to say to you guys, this is the first step. You scatter it, plot each point. And then you see, you know what? It looks like it could be on a straight line. Now, I want to say something to you. How's the slope of that line? So there is a possible negative what? Correlation. And does it look like that data is on a line exactly? I say no. So I don't know. It might be strong, might be weak, but it looks like there could be a negative correlation. I'm going to proceed. And do we have any outliers, you think? Any values that stick out heavily? I would say no. I would say no. So you guys know. So here's your step. Here's your process. So I guess here's step 2, or let me do something here. Yeah, this is the first example, the old way. So remember I said I used to give them all these X and Y values? They computed R. Let me just share with you guys this, okay? Let's go straight to the what? TI. No need to throw up. and all right, here's the TI. Here's what you have to do. You're going to have to enter the data into your calculator. Okay? Now, how do you enter data? Do you guys remember? It's, the same way you did before. Stat, edit, what? Edit. And then now you're going to have 2 lists. You say, what are the lists? L1 and what? L2. This is your scatter plot procedure. Okay? So I have to first enter this. So I'm gonna do that, but you say, what am I gonna do it for with all these data values? So I'm gonna go back up here with the data values, just so you guys know, and I'm gonna enter this. Okay? So let's go to the TI. I think it's awake. Yes. Go to, what was it? Stat, edit, edit. Now we gotta clear list 1. I'm gonna clear it. List 1 is all my X values. So it's all the values in orange. Those are the X values. They gave it to you as a row, not a column. I'm going to enter all the Y values in L2, and you guys are going to see what I'm saying here, okay? All right, so let's enter the data, okay? So let me see how this looks first of all. Yeah, we look okay. All right, let's do that. 3,175, hit enter. 3,450, hit what? Enter. 3,225, hit what? Enter. 3,985, hit what? Enter. 2440, hit what? Enter. 2500, enter. 2290, hit what? Enter. So these are all the X values in L1. How do I get to the Y values in L2? To the right, go to that right arrow. Now you can enter in L2. These are going to be all the green values, okay? So you're going to enter bivariate data. Now, 27 is the first green value. Hit enter. 29, hit enter. 27, enter. 24, enter. 37, enter. 34, enter. 37, you're going to hit what? Enter. Okay, this again is what? Entering the bivariate data. So that's really going to be what you do first. I'm going back here. I'm sharing with you guys what we just did. All the orange values, all the green values. Okay? Yep. That's right. That's exactly what it is. Good. Now, this is how we create the scatter plot. It's a bit tedious, and I have to go and remember again how to go through and do that. So for scatter plots, you got to open the stats plots menu. And you go, what? How do you do that? You're going to go to second Y, and then put enter. So let's go to the calculator and let's try to find that together, right? What do you think that is? You guys see it? Yeah, it's up in this corner here. I'm going to do that. Second, Y equals. That you see in blue? What is in blue? In blue on the calculator, that's the scatter plot. Okay? You see the word scatter plot there? On top of the Y equals in red? That's scatter plot. It's in blue. So you told the calculator, I'm in the scatter plot mode. Now you say, what do I do? Select on. Where is on? All right. Here you go. Press enter to access the plot 1. Okay. So we're on plot 1. You guys see that here? We're on plot 1. Select enter. There you go. All right. So we're accessing plot 1 settings. Select on. So I hit, what do I hit? I guess I hit enter. Now it's on. And after I select on, what do we do? Select the first chart option, scatter plot, then press enter. Enter names of the list containing X and Y. So really what you're doing is this. This picture here is a scatter plot. With me on that? Is X L1? Yes. Is Y L2? Then we're good to go. You see what I'm saying? So we're good to go. So then you say, okay, select the first chart option. We did. Press enter. Enter the names. We did. Press zoom. So now all I got to do is press zoom and then 9. Zoom and 9. So if you notice on this screen, there's nothing else to do, is there? So I got to find zoom. And you say, well, where is zoom here? Zoom is above the gray. You see these gray keys? You press zoom. What did I do? Oh my God, I screwed up. Second L2 is right here. There you go. Now I press zoom. And you say, what do I have to do? I got to go all the way down to what? Number 9. Because number 9 is called zoom stat. Again, a very odd phrase. What do you guys see if I hit zoom stat? What do you guys see there? You see the what? You see a scatter plot. Now, what I'm trying to share with you guys, that little process and procedure that's in your notes, you do over and over again, right? So you can do that, but it's supposed to mimic or look like exactly what you've seen here. Although, here, ladies and gentlemen, This was done in Excel. And that's the scatter plot. Does it look like the data fits in a straight line? It sure does. So we're good to go. All right. That's how you do a scatter plot. It's a little bit tedious. Not a lot. It's a little. Here's the procedure, though. And then here's the pictures. That first one. And then go to 9, zoom stat. You're going down here. Okay. Oh, press 9. I guess I did too many. There we go. That's what you should see. There's my notes. Now, here's where the rest of the work comes in. Okay, this is how you compute the linear coefficient R. And in fact, it's more than the linear coefficient. You're going to get a lot of pieces of information here. Okay, so really all there is today is how to do a scatter plot and then this, for the most part. Just two things. Scatter plot and then the rest. All right, you guys ready for this? Remember, when you set up the hypothesis test formally, okay, yes, you're going to have to use alpha being what? See this? 5%. And yes, what was the sample size? If we counted the data, how many data values are here? 7. 1, 2, 3, 4, 5, 6, 7. So n equals 7. Remember that degree of freedom was what? N minus 2, which is what? 7 minus 2. Degree of freedom is 5. What was alpha? 5%. Do you guys remember what key we used for those critical values? What was that critical value again? Yeah. We go second, distribution, inverse T. Uh-oh. What happened? What's that? Is it? Clear. Quit. Second, distribution. Go where? Inverse T. Okay. 5%. Is that true? So what was in the left tail, if you guys remember? If alpha is 5%, isn't this 2.5%? Degree of freedom is 5. Paste that in. Okay. So what is this to the nearest thousands? Negative 2.571. Remember, we did the default, 2.5%. This is the other critical value. There's two critical values. So I just want to let you guys know we have to have that set up because we got to draw our conclusion. Okay, so this is the formal hypothesis test. It's a two-tailed test. So, you know, you're doing step 2. Yes, you're using inverse what again? Inverse T. It's a small sample. And that's in your notes. Okay, so now you say, I'm going to skip the formulas. We're going to the TI. This is our scatter plot. We did the calculator, negative 2.571 to the nearest thousands. Right, so now we're going to do all the other stuff now. We got the scatter plot. It's kind of fun, I don't know, but let's go through this, right? So now you say, what do I do? How do I get the linear regression, right? How do we go about and do everything that we're doing here, right? This is the function that they want you to use. The linear regression t-test. So you're going to go to stat, test, linear regression t-test. You guys okay with that? Very simple. Let's do it together here. Stat test linear regression t-test. We got to find it. Where is it? I can't even see. What does it say?
F, no, linear regression t-test is F in the very bottom.
There we go. Is that it? Yeah. Lin reg t-test. Lin reg t-test. Now, what should be nice here is X is what? L1. That's correct. You guys with me on that? Y is what? L2. Is that right? List one for leave frequency 1. Don't know what that even means. What's the only thing I have to change? Yeah, this is to be what? Equal. This is a two-tailed test. And then just hit what? Calculate. Okay? And ladies and gentlemen, I'm sharing with you guys the procedure here. And let's talk about all this information on this screen. Okay? First of all, tell me, where do you think? Where is your test statistic value? Right here. What is T approximately? T is approximately what? Negative 6 point what? 393. Isn't that your test statistic value? You guys with me on this? Okay. Negative 6393. What does that mean on your decision rule? Yep, it's outside. So this is negative 639, whatever. This would be over here. Everything to the left of what? If you're to the left of that critical value, which you are, what's your conclusion again? You're going to reject the what? Null. Well, let's think about this, right? Isn't that where your test statistic is? Negative 6.393 to the left? You reject the null. What does it mean about, what's your null again? This is how you always set it up. You rejected the null. Remember, what's the claim always? Down here. But now, if you reject the null, what are you embracing here? The alternate. So what does that mean? There is a what? Linear correlation. Okay, so this is actually the formal test about this. So not too bad, just two things to learn. Scatter plot and linear regression t-test. Yeah, that's under the hood, this formal hypothesis, the formality of it. But that's how you draw your conclusion. There is a linear correlation. But let's read further because there's more information here. So we know the conclusion that there is a linear correlation. This even gets better, ladies and gentlemen. This is so amazing. I'm going to summarize here. I'm going to go back down here and say, yes, we know that this is a test statistic. Okay, we read what we typically read, but there's more to this. If I scroll down, right, let's scroll down here. Do you guys know that it even gives you the R value? What's that R value to the nearest thousandths here? See it in the calculator? Let me put this in our screen. R is right here. If I go to the nearest thousandths for R, the sample linear correlation coefficient is negative 0.944. What did I say that this was going to be close to? This is close to negative 1. Okay? Okay? So I'm just verifying by the R value being close to negative 1 that there's a kind of a negative linear correlation. We already know because it already passed our test. So what is the whole point of the whole thing anyway? Once you do that, we need what? We need this regression line. We want to be predictive. Okay? Now, here's the thing here. This is of the form y equals what? mx plus b. Okay? mx plus b. So you might say, Mr. Judge, where did you get these numbers? Negative 0.008 and then 54.695. Do you guys know where I got these numbers? For the regression line? Right here. But be careful here, okay? It drives me crazy that programmers wrote this and not mathematicians, but that's the way the world works. It's how it always works. This is why everybody hates math, because it's not math people who do everything. But I want to point this out. This is really the B. You know what it says A? From algebra, that's the B value. So they're saying the regression line really, if you're looking at these letters, this is going to be super confusing. Bx plus A. Okay, see what I'm saying by those programmers? They screwed it. I got A and B backwards, kind of. So this here, I'm going to say to you guys, this is M. And then this is B. And so you say, Mr. Judge, do I have, if I'm going to the thousands, 008x plus 54 point what? 695. Is that my regression line? And I'll say yes. So not only do you get all the other information, you even get the what? The regression line here. Okay, now why do you want the regression line again? So that you can be what? Predictive. And so they might now do this to you guys. What might they do? They're going to now say a question like this. They're going to say note. Okay? This is why you care about that. If x equals, what does x equal? Remember that? That's the weight of the car. So if the weight of the car over here measures, let's look at this list. Where's our data list? Right? I'm going to say if X is actually 3,000 pounds, what is Y, which is the MPG? You got to go to that formula. What was that formula? See if I still have it. Okay, it's right here. So you say, what do I do? You see this value of X right in here in orange? If the car weighs 3,000 pounds, put it in here. Let's see what this becomes. Y will equal negative 0.008 times that 3,000 plus the 54.695. It's almost like you should just approximate that weight of 55, you know. But let's see what this is. You guys see this in the TI? Let's take a look. So I can quit. Negative. Make sure you hit the negative. Don't hit subtraction. Negative what? 0.008 times 3,000. Really plus 55. 54.695. What is the MPG approximately if I go to the nearest tenth, maybe? Right? Yeah, we could do that. Well, tenth, 30.7 MPG, I guess, which is 31. So that's what they mean by being predictive. When the weight of the car is 3,000, you can expect to have a 30.7 or 31 MPG. It's probably better to go to the whole number, only because when you buy a car, you don't see the decimal, do you? They give you that nice whole number. They say, 31 miles per gallon. But there's a linear correlation between the weight of a car and what? And the fuel consumption, MPG. That's the process, ladies and gentlemen. And this is something that people invest a lot of time and energy into: linear regression and linear correlation and regression. Lot of time and energy. We want to know if there's a linear relationship between everything. So trust me, it is worth showing up today. Anybody ever hear about this in the courses you guys take? You ever talk about linear correlation? Yeah, once we talk about it, you'll probably hear it more. It'll probably now ring a bell and go, I've heard that word before. A lot of linear correlation relationships here between things. Huh? Yeah, in psychology, you should probably definitely hear it. Any sort of scientific course, I should take that back. Any scientific course, even a lot of the other courses, hard science, what do they call it? Hard science, soft science? I don't know. Well, in STEM courses, but like psychology is not in STEM, Social science courses, you're going to see some of that. Business courses, definitely. A lot in business courses. Like if you guys know, you know telemarketers? Do you guys hate telemarketers like me? I shouldn't say I hate them, but yeah, I try not to. Yes. Because there's a linear correlation between the number of calls they make and the amount of money they make. I'll say that again. In sales, definitely, without a doubt, they do this all the time because there's a correlation. And that's the simple reason. So you guys get to understand the world around you, which is the whole idea of math anyway. So you can study and understand the world around you. Jeez. I mean, imagine if politician X, we won't even name names because people get so sensitive these days. Politician X says, you know what? I'm not going to invest in education because it's never helped me anyway. It brings to mind a lot of things. We need more knowledge and information and free thought and exchange of ideas without people getting angry and upset, jealous and hateful. Amazing. But this is that first example. I do more than one, of course, and when you first see one, yes, it's long. You give people the background. Yes, it's long. But as you do another, it's shorter, and then do the third, it's shorter and shorter and shorter. And then the good news is, like I said, I decided yesterday. Actually, I decided late last night, and then I did it this morning because I made a note. Actually, yesterday I made a note to myself. I said it out loud, but I was hoping I hope nobody caught it. But I did it. What did I do? Not a formula sheet, but a what? A TI sheet, because that's kind of that's replaced the formulas. Notice all the formulas I showed you guys that you kind of were throwing up and you go, ooh. Then I said, just do this in the TI, don't worry. That your biggest problem is going to be just entering your data and finding what else to click. But it's important for you to know why you're doing it. It isn't just, why do we do this? To see if there's a linear correlation. And if there is, get the regression line. And when you do, you can be predictive. That's the whole idea. And then when you take the other courses, you might learn about other techniques that exist for other phenomena. Because there's more. There's a lot. You could get a PhD in this stuff. No? You don't want a PhD in this stuff? In statistics, yeah, you could get a PhD in statistics. Get a PhD in data science. You can make a little money. Data science is big right now. Yeah, you guys, I got to tell you, I'm going to give you the story Escalante told me. Well, you are, but other people aren't. People are discouraging people into going into STEM. Well, it's not that smart. People go into STEM, if you want to know the truth, because I work with those people. It's not. It's just. It's focus. Making a priority. It's discipline. It's not a measure of intelligence. I work with these people. And I shake my head.
Well, I feel like that's a form of intelligence. You know, I'm not saying that people that don't go in STEM aren't intelligent, but I'm just saying that these people like working with science and math and medicine and engineering.
And
They're an area where you do need your like entire focus.
you know what? You know what I really want to learn how to do if I could? Play guitar. I played guitar as a kid. I thought I was going to be Eddie Van Halen. I was one of these 80s kids. Going to clubs in Hollywood. Seen a lot of bands. LA was the music mecca of the world back then. So I said, I'm not going to do my homework because I'm going to be Eddie Van Halen. Not really, but, So I spent all my time reading, of course, you know about that, and also playing guitar in the garage. And the truth is, I'm not very good. I'm not good. I wish I had a formal education in it. I'm not very good. It's the truth. That's my point. It's not my point. That's my point. I now need a set time for me to do what? To practice and play and get better and better. And who knows? I'm not going to be Eddie Van Halen. But I might be Daniel Judge. Because even Eddie Van Halen, if you guys know him, he could never be anybody else other than himself. He had a hard time learning how to be like other people, so he just focused on being himself, and look what he became. Himself. That's the thing. So I guess what I'm saying is if you want to get better at anything, it's even applies to me, put the time, energy, and practice, make it a priority. If you do, you'll make your progress. You guys know what I'm saying? So there are people that say, yeah, they like science. They like what this means. They like this. Give it that time and energy. Because I came from an art family and a military family. It's military and art. That's my background and family. My dad was an artist. You want to know what I shouldn't tell you guys because some people get mad. Somebody made a negative remark about me 2 weeks ago at a meeting because I said this stuff. They didn't like it. But it's the truth. Here's what my father used to say. Daniel, major in something that's going to feed you. That's what he used to tell me. He was practical. And I'm like, Dad, I want to major in guitar. And he started yelling at me. He goes, Daniel, that's not even a major. What you major in is music. Not guitar. There was Guitar Institute, in Hollywood out there. It's out there. You can. They're there. But he didn't know about it. So he yelled at me. He says, you major in music. And he says, and I don't recommend it because you may not eat. Like, whoa, this is coming from an artist? It's coming from an artist. My dad was an artist. My mom was an artist. My stepmother's an artist. My aunts are artists. My cousins are artists. In some cases. It's a crapshoot. Yeah. Well, I don't know. I have a cousin majored in art. She eventually wanted to do special effects. Went into, did some stuff in Hollywood. Worked on some movies. With the special effects. She did Apocalypto. You like that movie? It's a good movie. If you guys don't know, here's an interesting story. If you see my cousin, she's on the Mexican side of my family. It's that side. And how she looks indigenous. She looks Native American, actually. She has that look, So the reason I bring that up is because they were going to cast her in that movie. And there was a character in the movie, she told me, what was it? She made a costume for a cougar. So somehow in that movie, there's a person that comes out as a cougar. That was supposed to be her. So that was her costume. But she didn't have that Screen Actors Guild card to be able to work, and they couldn't get it for her. So she ended up just doing solely the special effects, but because she's also not very big or tall, I should say. But she would have fit in, she was gonna be that character in the movie. Just by being on the sidelines of doing it, Apocalypto. She worked on another movie that what else did she work on? That Benjamin Button movie with Brad Pitt. She put her art skills to work for her. She didn't have to go to school to do it, though. But one of the things they did was they took her out of that kind of art area. They put her in management because she had a degree in art. She didn't want to do that. She didn't want to be in management. She wanted to be in with the artists and do the work. She didn't want to deal with all that stuff. And I remember she brought pictures of like Brad Pitt. And because they had to do some digital stuff with him, she brought all these pictures. I shouldn't be saying because they signed this agreement, but it's probably okay. And and Brad Pitt, he has like bad skin. People don't know, and I got to see it. Like, oh my god, I was like, Brad Pitt has like really bad skin. People don't know this. They got that real down to every detail. And remember, she told me a story. She says, you know what he used to come in and say? Because they had to make Brad Pitt age. He wanted to age pretty like Paul Newman. And they used to kind of laugh when he wasn't around. Mm-hmm. Age pretty. He wants to be pretty. Like Paul Newman, That was the story that she brings. What do you guys think? Isn't that kind of funny? She even made the claim that Brad Pitt was hitting on her. So probably. She worked with a lot of different people. I have another cousin, her brother he's won a couple of Emmys. They're first cousins. They're sports Emmys. So he got into, how he put statistics to work for him was, I think he majored in, what did he major in? Communication, I think. And so he's taking these statistics courses and he started interning for Fox. And then he started doing the baseball side, baseball stuff. So he was he was like an assistant director of these baseball games. So he's part of the Directors Guild. So he does Fox Sports, and that's when they started using a lot of the statistics in games and stuff. So he was a part of a team there, but he's like the assistant director. He got to travel and do all these baseball games. That's what statistics did for him. My cousin, and now he's won a second Emmy, but he doesn't tell anybody. He says, the first one, everybody gets one or something. I don't know. But the second one, you got to earn. We got a second one. It was kind of funny, too, because I used to have it on my phone because during one of the playoffs games, when he got married, they mentioned him and his wife's name in one of the playoff games because he got to know a lot of the Fox Sports people that work there, broadcasters. So one of the playoff games, they go, congratulations to Matthew and Kimberly Saldana. They got married this weekend, blah, 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 blah. And, so it does, statistics and math does open doors for you. But people don't hold that as a priority. Oh, yes. It's everything in the medical field. There's a lot of researchers. Yeah. Read that, understand it. It's the backbone of really medicine if you want to know the truth. This is the backbone of it. And there's some examples that I have here and I want to get to and do all that nice stuff because it's beautiful, but it's the backbone of research. Remember, you could get a degree in some areas like in medicine even. And you're not even a doctor, but you're a researcher. That's what you use. Yeah. And they pay you. They pay you. They need you. Depends. I mean, you as a person, right? If I said to you, and I don't even want to say it because I'm like, I want to cross my, you know, there's some jobs you can have that's not very physically labor intensive. Maybe you like that. Maybe you want that. Some people don't, though. Some people need to be outside. And if they're not outside, they can't handle being inside. Depends on the person. But a lot of what I'm showing you guys here, these tools are used. I'm going to learn another tool that's coming up, Python, to program and to do the same kind of things I'm showing you now, but it's different syntax. It's not TI-84 syntax. And data science is a big growing field. People make a lot of money doing that stuff. So it is there if you want to do it. And it's limited by your imagination, but you got to do some time, put some time and energy into it and do the work. And you start to like it when you start to become making less and less mistakes. But you got to practice before you get there. So I'm going to give you guys a quick break here because we're going to practice when we come back from break. But I kind of talk about these things because, well, I know about them. And also, hopefully, it's kind of inspirational for people, you know, that you can kind of think there's nothing special about anybody that does this. You can do it too. And hopefully you do. All right, ladies and gentlemen, let's check this out here. There's another study time versus grade. See if you guys are back. We're going to try this out. Study time and grade here. Study time. Supposedly, that's what you can control. That's an X value. The Y value is the grade you earn. Okay, now notice this. They're going to say the bivariate data below are the study times in minutes. And the grades are in percents. Okay. Earn an exam. Use the 5% level of significance. It's always going to be two tails. To test the claim that there is a linear correlation between the study time and the grade earned. So I got here the alpha. And let's see it. What's the sample size? 1, 2, 3, 4, 5, 6. So n is 6. And remember, degree of freedom is 2 less. And if you did inverse t, for inverse t, this is the function key, just to let you guys know. In this example, I gave people the critical values. But let's see how this works now. So inverse t, second distribution, inverse t, and again, that's 0.025 because it's a left tail. Degree of freedom got changed to 4, as you guys can see. So now we're going to see if this is correct for critical values. And yeah, plus and minus, because it's two tails. Plus and minus that negative 2776. So as you guys can see, the critical values are verified. So remember, we got to do a scatter plot. But before you do that, we have to enter all of these into list 1. These are my X values. And then all of these into list 2. These are the Y values. Okay, so go to the TI. Now remember, how do you enter a list? It's going to be stat, edit, edit. But don't forget to clear out the last example. So go up and clear, come down, go to the left, up and clear it by the title, and now you're ready. So we're going to enter these values, okay? L1, L2. So here we go. These are the values that we enter. L1, 20, enter. 40, enter. 50, enter. 60, enter. 80, enter. 100 and enter. So this is an L1. Now for L2, 40, enter. 45, 70, 76, 92, 95. Okay, so L1 and L2 now have their data. So remember what you're going to need to do with this after you do this, right? We're going to have to sort this data. So do you guys remember how to do that? We're going to have to do this. I believe it's going to second. You're going to go to scatter plot. Remember that? It's in blue, scatter plot, there. So you have to hit, to get to that word stat plot. To get to stat plot, it's in blue. You have to hit second and that Y equals. That's really what you're doing. Okay? So it is on 1. So we just hit enter. So we're looking for that plot 1. We're going to hit enter now. Now remember, this thing has to be on. Then it has to be on scatter, and it is. Then it has to be on L1 and L2 for the X and Y, and it is. Now let's see if you guys remember. This is very simple. We're going to have to go to Zoom, I think. Is that true? Zoom 9. Yeah, you know what to do. Good. Zoom. And you go all the way down to 9. Zoom stat. Outstanding. You guys know. And take a look. Do you think that data could be in a line? I do. And notice if we draw that line, and do you see any sort of outliers? I don't think so. I think everything's pretty good. What do I mean by an outlier? An extreme value that's off somewhere. So notice how quick that was. You see what I'm saying? That's not too hard, is that right? All right, now let's go back to the sheet here. So it does look like the scatter plot is good. This is a formal hypothesis test again. You always set it up this way, okay? So it's always set up where H naught is going to be rho equals 0. H1 is rho's naught equal to 0. Verify that, yes, this is a two-tailed test, and these statements are always going to be there as well. Meaning the top statement is always going to be no linear correlation. The bottom statement is, yes, linear correlation, and yes, that's your claim. So this is a formal hypothesis test. If you guys are doing this in a science or non-science setting, you would have to go through and set up the hypothesis this way. And notice again, we did the default. Since alpha is 5%, we already seen how we got the critical values, right? Inverse T, two critical values. And it's set up completely the way we've always been doing it. Okay? Good. Okay. Anybody have any questions at this point? Not too bad? Yes. Because if it doesn't, and actually one of the examples, maybe we'll go to it next. One of the examples, just because you have data doesn't mean it's going to line up essentially in a line. And if you notice that it doesn't, then there's no need to do a test. There's no linear correlation. So that's kind of the first thing you do is just, hey, let's see if there is a linear correlation, if we can visually see a potential line there. And if there is, then you go to the formal hypothesis test. But if it's not there, you're like, why do we even care? We're not going to even do it. And I think the last example is that way. And I'll do that one next. But again, this is the formal R and T. You had to get R before you got T. We don't have to do that anymore. We're going to go to what? We're going to do the procedure in the TI. Okay? So let's remember here. Go back to the TI. So we're in the TI mode, and it's kind of simple in the sense that we go to now what? Stat, tests, linear, let's find it. Did I go past it? No. Linear what? Linear regression t-test. Small sample, T. Linear regression, T. Okay. Hit enter. And yes, verify. Isn't that the x coordinate L1 and the y coordinate L2? And then that is a two-tailed test. So go all the way down to calculate. So ladies and gentlemen, what's your test statistic value? What is T to the nearest thousandths again? It's the second line. It's going to be what? Is it 6.090? Double check. Okay, do you guys see the test statistic value? All right. Now, where does that number live? It is definitely to the right of that 2 point what? This is where this number lives. It's really probably further away, but the point I'm making is it's bigger than the what? The critical value of 2.776. That means we reject the null. What does it mean to reject the null? Cross out. Goodbye, null. So since the null's gone, goodbye, null, what did you embrace? The alternate, which is the statement that there is a linear correlation. That's the claim. So this is a conclusion. We have verified that you have a linear what? Correlation. Okay, I told you guys the process will be a lot faster the second time. So once you know there's a linear correlation, what's the deal? What do you want? What's the regression line? Let's go back. I don't think I have. Yeah, what's the regression line? Remember, the regression line is what you're looking for. y equals mx plus b. What's that line? And the TI is going to tell you. Oh, what did I hit? Let's go back. Okay, stat. I got to bring it up again because I hit something. Okay, let me go down. Now, a couple of things I want to remark about. You see this R value, by the way? R is approximately 0.950. Is that true? So isn't that close to 1? This is close to 1. However, I mean, it's not that close, but it's close to 1. That actually, the closer you are to 1, the stronger the correlation. So you can have a very strong correlation, you can have a weak correlation, but it's not as close as the other. Anyway, okay, what's the regression line? Remember this? It's y equals, and I don't have that here, but I'm going to write it down. Y equals, it's really going to be this form, bx plus a. So what I'm going to do now, and I'm going to say to you guys, this is the TI version. Y equals bx plus a. So that means y will be, here's your regression line, 0.768x plus 24.857. Okay? Now that is what you're really looking for, the regression line. And once you find out there's a linear correlation, there's your regression line, the best fit line. So you might say, why do I care about that? Because you're going to be predictive. So the amount of time students spend studying on a test definitely correlates to the grade they earn, correlates to the grade. There's a linear relationship. So if I said, what if you studied for 110 minutes? Okay, plug that in for x. So if x equals 110 minutes of study time, that's your independent variable. In theory, that's what you can control. Plug that in here. You can now find the grade you'll get. 0.768 times 110 plus 24.857. Okay, so what do you get for your y value? Oh, you're going to get a what? 109%. I guess there's going to be extra credit on that test. So that's the idea behind it all. Linear correlation, ladies and gentlemen, to be predictive. So that way you know how many hours do you study on your test. No, it's just a question. It's an arbitrary question. So I want to share with people this. I kind of want to know, hey, what if you got a 110, right? Or what if you study for 110 minutes? Then you can expect 109%. This is being predictive. So that I kind of made up. So I want to, let's put that there. I made up. It's not written in the question anywhere. So that's a good question you have. It's a very good question. What do you guys think? Not bad? Yes. Yeah. Yeah, it's actually called a strong linear correlation if it's really close to 1. Also strong, but they call it a strong positive, strong negative. So it's a strong positive linear correlation and a strong negative linear correlation. If it's actually 0.5, there probably is no correlation. It would probably, if it's like 0.5, it'd be like no correlation. Let me share with you guys, because some of these examples are really, I love these examples. Here's a computer sale example. But let me go down to, I think the last one from my memory. Because like I said, yeah, here's the regression line. I think I asked people, but I think this one might be, is it that one? Okay, let's look at number 8, by the way. But number 8 has extra information, so don't worry, we'll read it. Believe it or not, CSI, and there's some people that want to go into those fields. You know, they want to go into like forensics. You know, not bad. CSI, you're an investigator for whatever, law enforcement, I guess. So let's read what this is. Bivariate sample data below represents the shoe print size at the crime scene and the height of the convicted male criminal. Good. It's a convicted male. So height, represents the shoe size. So here's your X. See that first line? This is the shoe size. Right? So they're trying to see, is there a correlation between your shoe size and the height? You guys know what I'm saying? And I don't know. Have you ever seen small people with big feet? And big people with small feet? Anybody here work in a shoe store? Did you see that kind of stuff? You were that. Tall girl with small feet. Do you like that? You're okay. Is that small, ladies? Is it small? Woo. How tall? How tall is she? That's kind of for, I guess, average height for women are like 5'5", I think. Interesting. But this is an example, just so you guys know, that is essentially along those lines. Like, is the shoe size correlate to the height? But this is for men. But let me double check. Let me be careful here. I want to read the shoe print size, not the foot length. Notice there's a little bit different. That's interesting. Because that kind of makes sense. You guys know what I'm saying? Because this is a crime scene investigation. People don't walk around necessarily without shoes, although they could. You guys know what I'm saying? So they're looking at, like, I guess they look at the shoe. So this is saying, look at the shoe print size, not the length of the foot, which is different. It's the shoe print. So I did highlight that correctly. And then the height of the convicted male. So this is a male thing. So this is down here, height of a convicted male. Kind of reminds me of that Night Stalker. If you guys remember that, you guys remember? His shoe, the controversy. His shoe was he used to leave these shoe prints, evidently at a few crime scenes. Very rare type of shoe at the time. Very rare. No, it wasn't a Jordan, but it was something, was it an Adidas? I don't remember, but there's some controversy about it all. See what happened? Here's the story. And it's a little political, but don't look into the politics of it. Evidently, what happened? Such a rare footprint, the investigators had information about that footprint, and they're trying to track down the location and who the shoe was sold to. And I guess who would happen? Investigators let Diane Feinstein know about that information. And you know what she did? She had like a press conference and she told everybody. You know what happened? Evidently, he he changed shoes. He got rid of his shoes. They think they think he threw it off the San Francisco Bridge. So in other words, that link to him by shoe, which is a very rare shoe, because if they caught him, they found those shoes, they can now link them to the crime scenes. See what I'm saying? But now he got rid of them, so you couldn't find the shoes and link them to the crime scenes. It's a very famous story about the Night Stalker. Yeah, they did. They caught him out here in East LA. Oh, you guys didn't know about? Did you know about that? Yeah. Caught him. It's a documentary. It's a long time ago. Documentary. Yeah, stay away from Netflix and documentaries. They caught him. They caught him out here in East LA. Yeah, he was trying to rob somebody. I think he hit this guy's wife, and the guy came out. You know, he hit his wife. The guy came out, and then the whole neighborhood came out, and they seen his picture on the news. They go, oh, "That's the killer!" And they caught him, and they beat him up, and he was trying to scare everybody, but he didn't. You know, it was in daylight. You know, if it was nighttime, it's a different story. But he was doing all this stuff in daylight, and they got him. Interesting story though. If you watch all that stuff, it's interesting. But that story about shoes is real, is what I'm saying. Crime scene, ladies and gentlemen. This is how you could use this stuff, and you guys don't realize. You go, this crazy course in statistics. Look at that. It could be you. Maybe you guys want to be that crime scene investigator. Maybe you like that. It's somewhere in your mind. Yeah. There you go. This is what we're talking about. This is your question. Jeez, this is for you. There you go. And there's nothing stopping you from reaching your potential. You have to always remember that. You know, you have a destiny. Why would you not have a destiny, right? Why would any of us not have a destiny? We have a destiny. It's going to help you reach your destiny. Yeah. Then you could read your... Remember, this is two tales. Say, first I have to read this stuff to get to your destiny. Okay, let's verify this. Remember this? If the sample size, we got to know the sample size. We're going to verify the critical value, just so you guys know. 1, 2, 3, 4, 5. The sample size is 5. For this process, remember, it's n minus 2. And you're going to do inverse t to get those critical values. So I just want you guys to go through this here to reach your destiny. And let's scroll out. Second distribution, inverse t. Okay. And it's still set at 0.025 because this is always two tails, remember? You're just changing the degree of freedom because your sample size isn't, you know, it's variable. So that's negative 3.182. Is that what I have on the list here? The answer is what? Yes. Okay. So we're going to remember, before you do anything, I just want to verify everything that we have here. Okay, because you can put that in your notes. Remember what you always do first. What do you do first? Always. Scatter plot. Because why would you check everything else if there's no visual confirmation of a line possibly being there? So let's enter our data. Remember, enter this data here. Yeah, so you're going to go to, where is it at? Stat, edit. It's already there, but we have to clear. Okay, L1, that's the orange. 29.7. 29.7. 31.4. 31.8. 27.6. Okay, let's go to the next one. Okay, L2. Whoa, I think I screwed up. Okay. Let's do it again. Stat, edit. Who knows? There we go. Ow. I guess it's the first value, right? Let me double check because I can't see. It is 175.3. 177.8. 185.4. 175.3. 172.7. Okay, did we enter everything? Yeah, it looks like. No, yeah, we did. Sorry, we did. Okay, you guys okay with L1 and L2? Now remember, what do we do now? We're going to do a scatter plot, right? So second, why? Because it's in blue. And yes, it's number 1. L1 and L2. Everything is pretty much set so you guys can see that here, right? It's on. It's the first one. X is L1, Y is L2. So now remember, what do we do? I know you guys know. Zoom 9. Zoom stat. Zoom 9. Zoom 9. What? What do you guys see? Yeah, there's a couple of ways we can go. There's 2 options at this point here, so you guys know. You could look at this and you say, you know what? There's no what? Linear correlation. Because this is actually what? What should we say? This is actually a picture where the scatter plot does not is problematic. You guys see what I'm saying? So you can say there's no linear correlation. However, again, I know this is a very small sample. Okay, it's like 6 values. Maybe you have 50 values, and that's not going to be an inverse T. It'll be inverse. You guys know. But for these questions you have in your book, right? For what we're doing, you have an option. You can probably say, you know what? I'm going to get rid of an outlier. That you see that point on the upper right, and then you now have a way to go about things that there might be a linear correlation. So yeah, you can get rid of that outlier. It's the second to the largest X value. And I would say, what number is that? I think that's 31.4. So, I mean, if you wanted to and you create an argument, you're going to say no linear correlation. I would say do that because it's such a small sample and it's an exercise in seeing the fact that you don't always have a linear correlation. But I would say there's a good case for that being an outlier because there's only one value. Okay, there's only one value. So that's an outlier. See what I'm saying? So if we throw that outlier out, because that's the second to the largest X value. You see how I'm reading it to the right? That's the X values. The second to the largest. And then it's going to have that 185, the largest Y value. So let's try this again just for fun. But I want to share with you guys that. If you've seen it was really scattered, like the picture I drew you, then you can say no scatter plot. But that actually looks like to me like an outlier situation because there's only one value. See what I mean? So if you had one or you had 2 values that were kind of off, you might get away with throwing those out. So if I go back now, I'm going to go back and do this again, okay? And I'm going to throw out one of the values. So I have to go to my list. Stat, edit. Let me do this. Look for 31.4. Delete. Where's my delete? There you go, delete. Okay, and the other one was 85. I'm going to delete that. You guys with me on that? See how I deleted those two? I just hit delete. Now I'm good. I want a scatter plot. Let's see it now. Second, Y. Yes, it's on 1, L1 and L2. Everything else is good here, right? What do you hit? Zoom 9. Zoom stat. I don't know. Maybe that's something that looks what to you guys? What do you guys think? Still looks bad. We're going to stick with what? No linear correlation. We can't go down to 2 or 3 data values, although we could, but probably need more data values to start to really throw out outliers successfully. Yeah. Yeah. Because it looked like that was more in line with the other data values. An outlier, remember, is that 1 or 2 values that are really off a line. That's why. So anyway, I would just stay here, no linear correlation. But technically, what the book is saying to you guys, yeah, you can throw out outliers. Remember, that was part of the process. Anyway, okay, let's go to another one of my favorites, in case you guys didn't know. Now, I've never been to New York. Anybody here been to New York? Anyone? One person? You been to New York? Did you try the pizza? That's what I hear. That's what I hear. Oh. That's what I hear too.
There's literally no difference. They use the same ingredients and everything, like, because it's no water from New York.
It's the water.
It's the water, guys. It's the water.
That's what I hear. Yes.
I wonder what the pH is. I wonder what the pH on that is.
I don't know, but I have heard, because this is something, it's probably multiple factors. But, it's kind of like in New York, making pizza is an art. People love that, and they want to perfect it. And there's history behind it. Kind of like in LA, if you said, what would you find in LA that's really good and you're not going to find anywhere else? Tacos. Everything tastes the same. Well, tacos, believe it or not, if you go out to other cities in the U.S. and you go, it's Taco Tuesday, I think I want to go find some good tacos. You want to know something? You're going to be disappointed.
California, trying to have good Mexican food.
Right. It's not, even in states, even in locations in California, is like, oh, man. It's like, go to Reno or something. Okay? Go to Reno and look for tacos. I know people, when they come from Reno and LA, the first thing they do is stop at King Taco. I know. I hear you. I know. I hear you. I hear you. I know. I hear you. That was not. So you worked there. So was the meat, am I right? Was it like frozen? Yeah, I told you. I knew it. Everything's frozen. Are you serious? Wow, everything's frozen, huh? Everything's processed. Do you guys know?
The only thing I give credit to is the rice. We make the rice.
That's the only thing that's made fresh?
And atole. That's it.
Sounds about right. Well, I told you guys my secret taco place down the street, and it's fresh there. You can taste it.
That's why I go to like the
Yeah.
tacos, because you see them being
Yeah, exactly. Exactly. Well, there's a place that the old Pep Boys. Look through your notes.
I write it in the front. I said,
It's where Pep Boys used to be. The tire portion of Pep Boys is still there. The trade-ins. Yeah. So McDonald's in front, gas station adjacent. There's a parking structure. Maybe, yeah. Maybe. But what you're going to see is McDonald's on a corner, gas station on a corner, the parking structure for the metro. And it's where Pep Boys used to be, but the tire portion of Pep Boys is still there. But the store of Pep Boys is not there. Anyway, it's in the parking lot. And they're really good. Yeah.
I like them because they're all colored. They're like uniform. Every day they wear a different color, like green, red, yellow, orange.
Oh, I haven't noticed that.
And it's a team. Yeah. Every
Good.
time I drive by there, I was like, wait, and my sister's the one that put it out there. Look, they're wearing a different color today. I was like, what? Yeah, they've been wearing like t-shirts.
Yeah. Well, you know what? When's I don't know if you've noticed since you work there. When's the only time you're ever going to see King Taco empty at dinner time?
Nothing. People are ordering tamales.
I was there at dinner time. King Taco, nobody was there. It was empty. That's the Third Street King Taco.
Oh, I didn't work at Third Street.
You ain't going to believe me. I think I might have took a picture. No, it was actually the Dodgers World Series. Dodger World Series game. Dodger game. Dodger game. It wasn't even a Mexican holiday. It was Dodgers. It was a World Series game. I had to get food before the game started, and I showed up, and I'm like, oh my god, I'm not gonna watch the start of the game. You know, I was so mad. Nobody was there. I took a picture and I sent it to everybody I knew. King Taco empty. True story.
Everybody else literally told me.
True story. But you know what? Pizza in New York. Here's what I hear. Pizza in New York. So good, evidently. Because it's an art. Number one, the locals, it's an art. But I've heard the water might be something that's... some pizza places, there's a pizza place out in LA that imports water from New York. Just to make their pizza. Like to make the pizza dough and everything.
That sounds like homeopathic water, like they water it.
I don't know. The water in New York is supposed to be really, really good. I hear.
It's because they're piping so old.
But the churros are dry as hell. Do
What?
not get churros from New York. That shit is
That might not be.
I'll say it's like a cast iron pot that has all the flavors. They're old pipes.
Don't know. Don't know. Do they get it? Do they get it at Niagara Falls or something? Don't know. If you talk to people from New York, I have colleagues who are from New York. I used to share an office, and that's what he says. It's the water. I go, what's in the water? He goes, no, it's really good water. It's better than anywhere else. Who knows? Who knows? That according to him, New York is the place for the water. I got to double check that. You guys might want to Google that, look it up, okay? But evidently, there's something more to pizza. The Subway fare and pizza.
Oh, the subway is pretty cheap, and it's I'm really jealous of New York because they have a really good subway system. I mean,
Yeah.
curious, but you know.
Mm-hmm. My daughter visited New York. She said she'd live there if she could.
Oh, not me. No, I would not. But
That's what she said. The winters probably are brutal.
my dad went there for business.
Yeah, she's a little bit. She's that kind of kid, fashion, you know, girly girl fashion. You know what I mean? That girl.
Look outside the window, have a view.
Yeah, she's a fashion girl. And anyway, I don't know if that's the reason, but she said, and she says the pizza's great, but there's a connection between pizza and Subway fare. There's people believe, that the cost of a slice of pizza versus the cost of a fare for the Subway, there's a linear correlation. So what you're looking at is a sample of data now from different years. Okay, you got what? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 is the sample size. What's the degree of freedom, if you guys remember? Good. Degree of freedom is 7. Now they're going to say to you, they want you to what? Use the 1% level of significance. They changed it on us. It's either going to be 1% or it's going to be what? 5% for this linear correlation. So in other words, if alpha is 1%, remember using the default 0.5%, which is 0.005, inverse t. So I'm just going to verify here again, inverse t, ladies and gentlemen. Let's verify that the critical values that I indicated are correct. Okay? So this is how you get those critical values. Remember, you want to be able to do that. So second distribution, inverse t. And I think I have to clear something because that's not right. Quit. Second distribution, inverse t. 0.005. Degree of freedom was 7. Okay, let's paste this here. So we got negative 3.499. The digit to the right is a 4. So it looks like, Mr. Judge, you did not approximate right. Okay, that's should be negative 3.499. And it's plus or minus because it's 2 tails. So let's double check. Wait a minute. If I go out to the, what do I go out to? Thousands here? 10, 20, yeah. If I go to the thousands, it's 499. If I go out to the hundredths, it's 350. Yeah, whatever. No. 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 You want to do both because it's a two-tail. Do both. Do both. Plus or you can do plus or minus. Just like it says here, you know. Because in fact, there's two what? There's two critical values. Anyway, and this is 1%, so this is kind of what we're doing. But remember, before you even do that, what do you want to do? You don't even want to start, you don't want to go there. You always want to do a what? Scatter plot first. Hopefully there's a linear correlation. Okay? So I'm going to enter this. Remember, how do you do that? You go to Stat, Edit, and we got to clear this out here. So I'm going to hit Clear up, go to the title. Go up to the title and hit Clear. Okay. 0.15, 0.35, 1. This is like $1.25, so you guys know. So yeah, it looks like our pizza slice is increasing. Let's try this out, 2.3. So we got this point, what, 1.5, 0.35, 1, 1.35, 1.52, 2.25, 2.5, 2.75. So, okay. We entered all of the data bivariate. Okay, remember, we want to do a scatter plot. So, in blue there, upper left, where the gray keys are, is a scatter plot. Now, what does it say? Can't see that? Yeah. Well, I think they call it, do they call it scatter? What do they call it? Stat plot? Weird. Never take a stat plot. Come on. Oh, these programmers. Okay, stat plot. It's on 1, yes. L1 and L2, that's not going to change. That has to be on. That first thing, by the way, is a scatter plot. Anyway, and then L1 and L2, and it looks like we're good. What do you hit again? You guys know this. Zoom 9. Zoom, and then zoom stat. I wish I would say scatter. So what do you guys think about this data? I would say to you guys this. Let me mention this to you about this data that you're looking at. That data is in a what? Line. Is that true? In fact, it really fits well on a line, don't you guys think? So I'm going to say this to you already without verifying it. It's going to be a linear correlation. And it's what we call a strong linear correlation. You say, why is it strong? Because the R value is going to be very close to 1. Because that data looks like it's actually a line already, right? So that's kind of, all the data is going to fit in a line. It's positive. So technically, we're going to call this a strong positive correlation. You're going to verify this with the hypothesis test. Pay attention to the test statistic and the R value. So, all right. So you say, okay, looks good. What comes next? The formal hypothesis. We already know we set that up. It's always H naught rho equals 0 where there's no linear correlation. H naught rho is not 0 where there is a linear correlation, and that's our claim. The level of significance was already given. We already found the critical values. We're good to go. Now, we're going to use a TI. Remember what you do. Stat, test. What is it again? Stat, test, and what? One linear regression t-test. They should call it linear correlation t-test. But again, the programmers gave the titles. X is an L1, Y is an L2. Yes, it's a two-tailed test. We just want to calculate. We're good to go. And ladies and gentlemen, let's pay attention to what we're seeing here. What is that test statistic value? What's the t value? 20 point what? 46 what? 4. You guys okay with that? Where is that at? Isn't that bigger than 3.5? That's actually off the charts. Would you guys agree with that? It is larger, and you guys can't see this, sorry. I'm writing it down. It's larger. This number is bigger than 3.5. Significantly bigger. What neighborhood? You're in the reject the null neighborhood. That test statistics is about 20. 464. You're going to reject the what? You're rejecting the null. What does that mean if you reject the null? You're accepting the alternate, which happens to be the claim that there is a what? So yes, that's your conclusion. You have a what? There's a linear correlation. That's right. You pretty much know it by looking at the scatter part. But this is a scientific proof of it. So, yeah, it's showing your work. It's actually like if this was your job, you have to be able to articulate numbers and process and not just say, well, look at it, even though you're right. So this is like the documentation or the proof that there is a linear correlation. Now, remember what I said about the R value? What did I say about R? It's going to be close to 1. And I say, well, how did you know that? Because when I seen the picture, that's practically a perfect linear correlation. Now, what is this? 0. What? 991 to the nearest what? Thousandths. So you guys know. And 0.991, that's close to 1. Remember, if I approximate to the hundreds, that's 0.99. That's almost 1. So this is going to be like the strongest linear correlation that you guys see here. This indicates what we call a strong positive linear correlation. Strong positive. You can have a weak positive. You can have a strong negative. You can have a weak negative. Anyway. So there you guys go. What comes next? You say, why do you do this anyway? Because you want the regression line. The best fit line. You want the equation that can be used to be predictive. So in some books you have regression line, best fit line. You say, well, how do I get that? Well, remember what I shared with you guys here on the TI. The TI describes it, not y equals mx plus b, but y is bx plus a. It's a Another one of these programmer things. That's one of the reasons why there's confusion in math, because everybody that describes it doesn't really use the notation correctly. So let's write this down. Y equals, what is this? 1 point what? 0.11x plus, what's the A value? Oh, it's negative point what? Negative 0.011. So that negative here, you could just say subtraction. That's your regression line. This is the actual equation. So why do you care? So you can be what? Yes. Now, well, this is what I'm getting at. So once you get down to here and you say, okay, I got the nice equation you got. What they're going to ask you probably is this. They can say, they're going to be this is now the predictive portion. So that's why I'm going to make up an X value. So if X is, in other words, let's say pizza costs 50 cents. Then what's the subway fare, which is Y? Remember, X is the cost of a pizza. So you go, well, what do I do then? Well, I'll go to X. What do I replace X with? 50 cents. So let's see what the cost of the fare would be. So if a slice is 50 cents, let's see. Let's quit. So we have to put 1.011 times the 50 cents. Now that's plus a negative or minus 0.11. And this is money. Is that true? So what would you think you'd say as money? It's about 49 cents, right? Because you can't tell somebody, hey, you need to pay $0.4945. You can't do that, okay? It's going to have to be, to give an answer that makes sense. Like, notice what made sense if I gave you the cost of a pizza in a realistic dollar amount. This is the cost of the subway fare in a realistic dollar amount. So, ladies and gentlemen, yeah. I was just going to say, I don't know. Are you getting better and better with the process?
Where would I go wrong if I don't get the t-value?
Well, in theory, if you don't get the right critical value, once you get the test statistic, you can draw the wrong conclusion. So the whole purpose of getting a critical value here, when you set this up formally, right? Is that where was it? Yeah. I always ask for critical values. It's like for hypothesis testing. If you notice, I say, what's the critical value? What's the test statistic? What's the conclusion? So I ask for all those things, but yeah. So the question is, what if you don't have the right critical value? Does it matter? I'd say then you don't know what the conclusion is.
I got the right critical value,
Okay.
but when I went to the last part of Zoom stat,
Yeah.
I didn't get that.
Well, okay. What you're referring to is the plot, the scatter plot, right? So what you're saying is this. Here's go through the process. Second, what is that? Stat plot. It has to be on L1 and L2. It is. Then it has to be on L1 and L2. Has to be on that first type. This is a scatter plot, by the way. These are different things. I think this is a box plot, but anyway, it is on scatter plot. But you have to hit zoom, and then number 9, and that's all you do to get the what? You have to show it to me. Let's see. Just bring it in. Let's see. Okay. So what I'm going to do here is I look that over. I'm going to have you guys start on this question. Advertisements and car sales. Now you can understand those other situations. have you guys try this out. We'll give you some time, okay? On your own. See what you guys get. All right, let's try this out. Okay, so here's kind of, again, when you read this, this represents the number of what? Number of advertisements in a month. So that's my first variable. Versus the number of what? Cars that you sell. So that's why you might see why they always bug you with advertisements. Okay? So all of these values are X values. And all of these values are Y values. So if you plug this in, remember bivariate data, stat, edit, clear things out. L1, 6, 20, 0, 14, 25, 16, 28, and 18. Okay, so now for the second list. 15, 31, and 10. 16, 28, 20, 40, 25. Okay, so realistically, again, you just entered all your data. Okay, so you want to do the scatter plot, right? So you're going to do the scatter plot. Did they fix it? What was it?
You gotta go to Windows and then fix the min and the max.
That's what I thought. Yeah, that's what I thought. I've had that before, that issue, but I forgot how to fix it.
I thought it came like that, right?
No, you must have did something. You touched something and it changed things, because that happens. I did that too. So anyway. Oh, good. Now you can help everybody if that happens. Show me how to do it. So there's now remember, sometimes those scatter plot windows look weird. So I guess you got to go to what window, huh? And change the min and max. Yeah.
And then you have to go to that point that's off and then take that point out.
I never heard that part. I thought it's just fixing min and max. Anyway, so let's do the scatter plot in this so people can see. So remember, we got to go to, it's really called stat plot here. So stat plot. Okay. Looks like everything's okay. L1, L2, it's on that first. Remember this, it has to be on this right here. That first one. And if you've been doing this over and over again, it will be. So anyway, now hit zoom and then 9. So as you guys can see, pretty straightforward. And I don't know, what do you think about that? Does that seem like there's a... I think that looks like there's a linear correlation. Data seems to be in its positive uphill, you know. We'll see what the R value is, but that looks okay. All right, what do you guys think? Look okay to you to proceed? So you say, okay, once you proceed, what are they telling you? You know, they're going to say use they're back to 5% level of significance. We have N. Let's do the sample size. 1, 2, 3, 4, 5, 6, 7, 8. So if N is 8, degree of freedom is always 2 less for linear regression and correlation. So I have a 6 degree of freedom. Okay, so this is a two-tailed test. So I'm going to try to get my critical values again. So half of 5%, and this is two tails, you guys know will be, so like alpha over 2, using the default, half of that 0.05 is 0.025. So, and I guess you guys can't see. So there we go. Inverse what? Inverse T. Inverse T. So second distribution, inverse T. I think we did not clear it. Yeah. You kind of have to quit. So second distribution, inverse T. 0.025. Degree of freedom is 6. So this is negative as your critical value, right? Going out to the thousandths. Negative 2.447. Negative 2. Now there's 2 because it's a two-tailed test, right? So notice this. My critical values that I indicated on the sheet were correct. So here you go. Of course, we're not going to do the old formula version, but notice this, ladies and gentlemen. We have the right critical values. Yes, alpha is 5%. We did the default area to the left. And we set up our hypotheses. H naught is no linear correlation. Rho is 0. Rho is not 0. There is a linear correlation. That's the claim. So we just need to now compute our test statistic and see where it lives. Is that right? All right. What do we hit in the TI? Do you guys remember? We go to what? Stat test. Go down to, linear regression t-test, F. So yes, it's on L1 and L2. It's a two-tailed test. Yes, we calculate. So everything is already set for us. Okay. So what's our test statistic if we scroll in? What's the test statistic on this? T equals what? 5.762. This is what we're looking for. So that is to the right of the critical value out here. Okay, so it's really to the right. And in fact, anything larger than the 2.447, that's to the right of it. We reject the what? You're rejecting the null. So what does it mean to reject the null? You're accepting the alternate, which is there is a linear correlation as claimed here. So, normal process. So we verify that there is a linear correlation. And then after you do that again, remember the whole idea is to get a regression line. And the TI says y is bx plus a. Right? Bx plus a in the TI. Right? So you go, okay, let me go to y is bx plus a. And what is that going to be now? What would you guys, if they say, what's the best fit line, regression line? 0.970. That's B. It's not 0, it's 1. Is that right? 0.971x. And what's your A? Plus 7 point what? 716. This is the what? Regression line. Also informally known, you'll hear it as best fit line. Sometimes they say, what's the best fit line? Meaning the line that fits the data the best. Kind of reading it backwards. Now, you might say, what do I do with this line again? Well, you could be predictive. So if I said to you, guess what? I want you to advertise next month 12 advertisements. Now, I just made that up. So if I said to you, hey, 12 advertisements, if X is 12, that goes right in here in the equation. Tell me how many cars that's going to guarantee I sell. Okay, you guys see what I'm saying? 12 advertisements gives me how many car sales? Yep. So you plug that in. 0.971 times the 12 plus 7.71 what? 6. So again, are cars sold in whole numbers? So I would say what makes sense is if you say, you know what, you're going to tell your boss you're going to have what? 19 car sales. So 12 is the number of advertisements. Those are the ads in a month. This is the car sales. Because there is a linear correlation between the number of advertisements and the cars sold. Easy breezy, lemon squeezy. Easy breezy. What do you guys think? I think so. I think so. What do you guys think? You okay with that? Well, let me remind you. What did I put? Remember, I keep telling you guys. I'm going to be a reminder because somebody might have just woken up right now. Your final exam is tomorrow at what time? Well, it's at 11, but I'll be here early in case you want extra time. Well, I'll be here at 10 if you want. Is that too early? Sacrifice? That means you got to wake up at 9:45. Is that right? Earlier. Way earlier. 5? How many? They'd be so happy. Who's going to watch them? Who's going to watch them? Bring them to class. Not those kids?
They're behaved, but embarrassing sometimes.
Oh, yeah. How old are they get?
They're both 7 right now.
Mm.